Welcome to the second day of Summer General Physics. In this sixth video, we'll be taking a look at some acceleration example problems. So the first example we'll look at pertains to the video that you just watched on the Apollo 13 launch. Actually, it was the Apollo 13 movie, which was a dramatization of the Apollo 13 mission. And based on the movie, we're going to ask the question, what is the acceleration that the astronauts experience as the rocket lifted off? So this is the first installment of something I like to call Physics Goes to the Movies, where we take a look at a movie clip and analyze it to see if the physics is correct or what kind of physics principles we can get out of it. So in this movie, one clue that we're given as to the acceleration is that you heard Mission Control say you've cleared the tower in 13, meaning they had cleared the tower after liftoff in 13 seconds. So based on that, what acceleration did they experience? Well, we're going to need a little bit more information than just the amount of time it took to clear the tower. But if you go online and do some searching, that information is pretty easy to find. So one useful piece of information is the tower height. So if you look online, the tower height is given as being 380 feet. So that's an additional piece of information that we can use. So if I take my 380 feet, I'll want to first convert that into SI units. So to do that unit conversion, I know that there's 3.281 feet in 1 meter. And so that means the tower height was 116 meters. But even there, I'm kind of getting ahead of myself. The first step in any problem that we should do is to draw a picture of our problem. So let's do that. So in our problem, the rocket was lifting off. So initially, let's just say this long part of the L is the tower. And initially, the rocket was sitting on the launch pad and it was not moving. So initially, it's stationary. The bottom is at the bottom of the tower. The top of the rocket is at the top of the tower. And then, once the rocket has launched, it moves upward. And when it clears the tower, that means its bottom is flush with the top of the tower. And so the rocket has moved upward, and now it has some upward velocity and is clearing the tower. And we know this distance that the bottom of the rocket travels is our 380 feet. Okay, so the next step in solving the problem is to make a list of the things we know, the numbers that we know, and associate those numbers with parts of the problem and with different variables. So one of the things that we know is we know the distance that the bottom of the rocket, and therefore the rest of the rocket, traveled. It traveled the height of the tower, so our delta x is going to be 116 meters. And it's okay that the rocket was actually traveling in the y direction, according to my picture. That's fine. We can use delta x as being the direction of motion, or delta y. It doesn't matter. The two in this case would be interchangeable. Another thing that we know is that initially the rocket wasn't moving. Initially it started off at rest, so my initial velocity was 0. The third thing that we know is the amount of time. We know that it took 13 seconds in order for the rocket to travel that 116 meters. Then we write down our unknown. What is the thing we're trying to find? And the problem is asking us about acceleration. So that's what we want to know. Okay, so now that we've written down the list of knowns and unknowns, we should pick out one of our constant acceleration equations to use to solve the problem. So if we go back to our slides and we look at our constant acceleration equations. We want to use a constant acceleration equation that has a change in position in it, maybe, of initial velocity, time, and an acceleration. But maybe we don't want to use one that has a final velocity because we don't know what the final velocity is. We probably could find it, but we don't have it yet. And it's not one of the unknowns we're solving for at the moment either. So this first equation, we probably wouldn't use that one because it has final velocity and we don't know that, and we want to know acceleration. Let's see, this equation doesn't have acceleration in it at all, so that's not terribly helpful. And then if we look at these other equations, let's see, this one has a displacement, an initial velocity, time, which we know, and it does have acceleration in it, so this might be a good candidate. These other two equations, once again, have that final velocity, which we don't know and we really aren't interested in. So I think I'll select this middle equation. So I'll write that down. Delta x, or the change in position, is equal to the initial velocity times time plus 1/2 at squared. And the thing I want to find is the acceleration. So the next step would be to solve this equation algebraically for the acceleration. The tempting thing is to just plug in numbers, but if I just plug in numbers, I'll be doing a lot more individual calculations with my calculator, and there's a lot more opportunity then to make some mistake that might cost me a bunch of time later. So if I solve this equation algebraically for the acceleration, the first step would be to subtract v naught t from both sides. So that would give me delta x minus v naught t equals 1/2 at squared. I want to get the a all by itself, since that's the thing I'm solving for. So at this point I could multiply both sides by 2. And so the 2 cancels on this side, and I can also divide both sides by t squared. Which makes it cancel over here. So now I have a formula for my acceleration. The acceleration is equal to 2 times, in parentheses, delta x minus v naught t over t squared. So at this point I think I can plug in numbers. I have a 2, my change in position is 116 meters, minus my initial velocity was 0, so that's 0 times 13 seconds. So 0 times 13, of course, is just going to be 0, and then I divide all of that by t squared, or my 13 seconds squared. So this then would give me an acceleration of about 1.37 meters per second squared. So that would be my solution to this problem. All right, so let's take a look at this second example problem. So in this problem we have a racing car which reaches a speed of 40 meters per second. It begins uniform negative acceleration, so that means it's slowing down, it's decelerating, which is a kind of acceleration, a negative one, using a parachute, and it comes to rest 5 seconds later. So in this problem we're asked to solve for two things. Firstly, what is the acceleration? And then how far does the car travel after the acceleration starts? So once again, the first thing I really should do is draw a picture. So initially my car is going really fast. So I have this race car, and my race car is going really fast. It has this initial velocity of 40 meters per second. Then sometime later, 5 seconds later, it comes to rest. So sometime later, my velocity is 0. It has stopped and is no longer moving. And the amount of time that elapses between these two states is 5 seconds. All right, so the next thing I should do then is to make a list of my knowns and my unknowns. So one of the things that I know is the initial velocity of the car. My initial velocity is 40 meters per second. I also know the final velocity of the car is 0, and the amount of time that elapsed between those two states was 5 seconds. Okay, so those are the numbers I'm given in the problem. What's my unknown? What am I solving for? Well, in part A, I want to know what is the acceleration. That is my unknown. So next, I would take a look at my constant acceleration equations. And if I take a look at these equations, I want one that involves the initial velocity, maybe the final velocity and time, and definitely has acceleration in it so that I can solve for acceleration. And looking at these equations, it looks like the very first one would work. It has initial and final and initial velocity, it has time, and it also has acceleration. So if I select that one, final velocity is initial velocity plus acceleration times time. I'll next want to solve for my unknown, which is acceleration. So final minus initial velocity is equal to acceleration times time, and then divide both sides by t. So that means my acceleration will be the final velocity minus the initial velocity over t. So if I plug in numbers, my final velocity is 0. The initial velocity was 40 meters per second. And the amount of time that passed is 5 seconds. So it looks like my acceleration is now going to be equal to minus 8 meters per second squared. So that would be the acceleration, the answer to part A. So part B of this example asks, how far does the car travel after the acceleration starts? It's a negative acceleration. That makes sense because the car was slowing down. And I want to know how far does the car travel from the initial starting point to the point where it stops. What is the displacement? All right, so then I need to start part of this process again and look at my knowns and my unknowns. Well, now A is no longer an unknown. I know what A is. A is minus 8 meters per second squared. And my new unknown is the displacement. How far does the car travel? So once again, we take a trip back to our constant acceleration expressions. And now it looks like we have a whole bunch of different ones to choose from, actually. We want to know the change in position, but we know so many things now. We could use really any of these equations that have a delta x in them, because we know the acceleration, and we know the initial and the final velocities. So how about we choose this second equation, where delta x is equal to 1/2 the initial velocity plus the final velocity times time. Well, it looks like this is already solved for my unknown, so I can just go ahead and plug in numbers. The initial velocity was 40 meters per second. The final velocity was 0, and the time was 5 seconds. So solving for displacement, I get a value of 100 meters. And that's the distance that the car would travel while it's slowing down and coming to a stop. Now you'll notice I could have used these other two equations, and if you want, you can check them out and see that they will give you exactly the same final answer. So here's a question for you. Let's say we have two cars that are moving in the same direction in parallel lanes along a highway. At some instant, the velocity of car A exceeds the velocity of car B. Does this mean that the acceleration of A is greater than the acceleration of B? Does that necessarily need to be true? Yes or no? So pause the video here and give this some thought. If the velocity of A is greater than the velocity of B, is A's acceleration also greater? All right, so now that you've given that some thought, we should take a look at this problem. We know the velocity of A is bigger than the velocity of B. So A is going faster than B. What does that mean as far as the acceleration goes? Imagine this scenario. Imagine we have these two cars that are going in parallel lanes, and imagine that this is car A, and imagine the truck is car B. They're in parallel lanes, and let's say that A is going faster than B. The car is going faster than the truck. But let's also say that the car has been on the interstate for a while. So it's traveling at 70 miles an hour, and it's been traveling at 70 miles an hour for quite a long time, for miles and miles and miles. What is its acceleration? Its acceleration would be 0. If it's traveling with a constant velocity, then it has 0 acceleration. Now imagine the truck has just come up an on-ramp, and it's only going 60 miles an hour, but it's coming up to highway speed. Its acceleration, therefore, would not be 0. It would be something greater than 0. And so the truck would have a higher acceleration than the car, even though the car is going faster. So in that scenario, the car has no acceleration. It's traveling at a high but constant velocity. But the truck's acceleration is non-zero because its velocity is changing rapidly as it's speeding up. So it's not true that the acceleration of A would have to be greater than that of B. So let's take another look or a recap of the ideas that we've looked at in this second day. We discussed how displacement is a vector, and remember, displacement is the straight line distance from a starting point to an ending point. And if you want to add multiple displacements, you have to add them as vectors. Adding vectors can be done a couple of different ways. If you just want to make a rough sketch, then the tip-to-tail method is a really good way to figure out how the vectors are pointing. So you take the second vector and put its tail on the tip of the first vector and then add them together. Or you can use the component method, which is a faster way to get a more exact answer. And that's where we break the vectors into their components and then add all of the x components together and then add all of the y components together in order to find the x and y components of the resultant vector. We also looked at velocity and how velocity is speed, but it's also direction, so it's a vector. We looked at the special case where you have constant velocity, meaning no acceleration, in one dimension, and in that case we can write down our constant velocity expression, that the change in position, which is the same thing as the final minus the initial position, is equal to velocity times time. Now this only works when the velocity is constant, when the acceleration is 0. We also discussed how acceleration was a change in velocity. You can get an acceleration by speeding up, slowing down, or changing direction. But if you have the special case where you have constant acceleration and your motion is in one dimension, then we can write down any of these constant acceleration equations and use whichever is most convenient for solving our problem. So this concludes the second day of summer general physics. Tomorrow, we'll start considering motion in 2 dimensions, and we'll also be looking at falling objects.